Dear students, welcome to the part 3 video of one-dimensional harmonic oscillator. So far we have defined the complete wave function of the harmonic oscillator. Now we will see the energy values of the harmonic oscillator. We have already seen that the wave function for the harmonic oscillator is satisfactory only for certain value of n of the exponent of the y in the equation 9 that we have already discussed in the part 2 video. And there we have seen that alpha by beta is equal to 2n plus 1. We have already defined alpha as 8 pi squared me by h squared and beta as 4 pi squared nu m by h. Therefore, alpha by beta comes out to be 2e by h nu. Now we will substitute for this alpha by beta. Thus we get alpha by beta, which is equal to 2e by h nu, that is equal to 2n plus 1, or E, the energy of the oscillator, is given by n plus half of h nu, where n, it can take values 0, 1, 2, 3, etc. and they are called the vibrational quantum number. This means that the energy of the harmonic oscillator is quantized. That is, energy is dependent on this vibrational quantum number. The energy of the harmonic oscillator is quantized, and this is contrary to the classical view. According to the classical view, the energy is assumed to be continuous, but in the quantum mechanical harmonic oscillator, the energy is quantized. The energy corresponding to different values of n, that is, for n is equal to 0, we will have the minimum energy E0, that is given by half h nu, and for n is equal to 1, E1 is equal to 3 by 2 of h nu. For n is equal to 2, E2 becomes 5 by 2 h nu, and for n is equal to 3, E3, that is equal to 7 by 2 h nu, and so on and so on. Here we can see that the energy separation, that is the energy difference between two successive energy levels, that is given by delta E, that will be always equal to h nu, which means that the energy levels are equally spaced. Again, the energy corresponding to n is equal to 0, that is referred to as the 0-point energy of the oscillator. So far we have discussed the energy of one-dimensional harmonic oscillator, quantum mechanical one-dimensional harmonic oscillator. Now we will see the plots of the wave function psi. In this picture, you can see the plots of the wave function, say psi 0, psi 1, this is psi 0, this is psi 1, psi 2, psi 3, psi 4, and it will be going like this. And this will correspond to the vibrational quantum number 0, vibrational quantum number V nu is equal to 1, vibrational quantum number n is equal to 2, n is equal to 3, and n is equal to 4. Here we can see that the wave functions are either symmetric or anti-symmetric with respect to the origin. Here x is 0, this is the origin, x is equal to 0. Suppose if we take psi 0, then this wave function is symmetric about x is equal to 0. That is, suppose if we take this as positive, then this will also be positive. If we move on to the next wave function, say psi 1, then we can see that this wave function is anti-symmetric with respect to the equilibrium point x is equal to 0. If we take this as positive amplitude, then this will be negative. Therefore, this is an anti-symmetric function. Again, if we take psi 2, that is again symmetric with respect to x is equal to 0. And the next wave function is anti-symmetric. Therefore, we can say that the wave functions are either symmetric or anti-symmetric with respect to x is equal to 0. Also, another point to be noted is that in the ground state, that is for the vibrational quantum number n is equal to 0, if you see the wave function, you can see that there is no nodes. There is no node in the wave function. However, if we move to the next wave function, say psi 1, and where the vibrational quantum number n is equal to 1, we can see that there is a single node at this point. If we move on to psi, the next wave function psi 2, where the vibrational quantum number is 2, we can see two nodes here. So in the case of psi 1, there was only one node, and in the case of psi 2, there are two nodes, and in the case of psi 0, that is a ground state wave function, there is no node. There are no nodes in the ground state. Again, if we move on to psi 3, we can observe 1, 2, 3 nodes. Therefore, we can see that there is an additional node at each successive state. Now we will see the plot of the square of the wave function, that is the psi square. Actually, psi square gives the probability density. We have already mentioned that the significance of psi square, that is a probability density, which is again a measure of probability. Here, the plots reveal that the particle in the ground state has maximum probability of being at the central position, that is at x is equal to 0. This is the point at x is equal to 0. Here this is x is equal to 0, and here we can see that the probability, the amplitude function is maximum at the equilibrium position, or x is equal to 0. But if we move on to psi 1 squared, then the amplitude function at the equilibrium point or the central position, that decreases. If we move to psi 2 squared, again we can see that the central amplitude function is less than the other two maximum amplitude functions. Therefore, we can see that as the state increases, as the wave function increases, if you take the square of the plot, we can see that the amplitude function actually falls at the equilibrium point. This is the case. See, there is a probability is minimum towards the central equilibrium point if we move towards the higher energy state. But at the ground state, say at psi 0 squared, there the maximum probability is at the equilibrium position. This is a quantum mechanical phenomenon. But as we move to higher energy, the probability moves towards the end. That is, for excited states, the probability increases towards the classical turning points, and this is expected from the classical results. That is, according to classical mechanics, the probability of an oscillating particle, the probability is at the extremes, while the quantum mechanical concept says that the probability is at the equilibrium central point. Therefore, it should be noted that there is a finite probability on the either side. That is, if we move from psi 0, psi 1, psi 2, we can see that there is an amplitude function at the forbidden region of the classical turning points. Here, the probability density is never equal to 0. That means that there is some probability of finding the particle at these extremes. However, there is no such clear-cut probability at the ground state, but still there is some probability, but this probability is very low in the case of ground state at the turning points. But as we move towards the higher psi value, we can see that there is a phenomenon called a tunneling or the penetrating effect towards the classically forbidden region. That is here in this position. That is, a particle can tunnel through this barrier. That is the meaning of this plot. This means that the particle can penetrate this potential energy barrier. This is actually the potential energy barrier, and the particle which is confined in this potential energy barrier, it is capable of penetrating the barrier and appearing on the classically forbidden region. This phenomenon is termed as the penetration or the tunneling effect, or we'll say that the particle can penetrate through the potential energy barrier. Now we will compare a quantum mechanical harmonic oscillator and a classical harmonic oscillator. The first and foremost point in the case of a classical harmonic oscillator is that the energy is not quantized. While in the case of quantum mechanical oscillator, we have seen that there appears what is called a vibrational quantum number, which can take values 0, 1, 2, 3, etc. And therefore the energy is quantized in the case of a quantum mechanical harmonic oscillator. Again, we have already seen that in the case of a quantum mechanical harmonic oscillator, there is something called a 0-point energy. That is the energy E0, which corresponds to the wave function psi 0, where we have got energy as half h nu, and that is termed as a 0-point energy. On the other hand, in the case of classical harmonic oscillator, there is no such 0-point energy. Another point is that the probability of finding the particle is maximum at the turning points. In the case of classical harmonic oscillator, the probability is maximum at the classical turning points, while in the case of quantum mechanical harmonic oscillator, especially at the ground state, we are talking about the ground state in the case of a harmonic oscillator, there the probability of finding the particle is maximum at the equilibrium point. That is a central position of the central point or the equilibrium point. That is a point corresponding to x is equal to 0. Again, the last difference is that the particle is always confined to the potential energy barrier. In the case of classical harmonic oscillator, the particle is always trapped within the, just like this, it is always trapped within the potential well, while in the case of quantum mechanical operator, in the case of quantum mechanical particle, quantum mechanical harmonic oscillator, the particle, even though if it is inside the potential energy barrier, it finds some way to penetrate outside or tunnel outside the potential energy barrier. Therefore, we can say that the particle, the quantum mechanical oscillator or the quantum mechanical particle is capable of penetrating the potential energy barrier. These are the four main differences between a quantum mechanical harmonic oscillator and classical harmonic oscillator. So hope all the points are clear to you. Thank you.